My report is the noise temperature compensation strategy for not finding MEMS gyroscope. I'm from Nanjing University of Science and Technology. It's divided into 5 parts. The first part mainly introduces the application of not finding and the principle of MEMS not finder. And not finding are widely using aerospace, ocean shipping, energy drilling, and base station, and so on. Common ways to find the nodes include compass, GPS orientation, astronomical orientation, and so on. But compared with above methods, high precision gyroscope can self-orientate by itself and is not affected by weather or transmission. Traditional gyroscope are occupying this application for a long time, but now the MEMS gyroscope with the low cost, size, and weight and power, and has reached the barriers instability under 0.1 degree per hour, and has the ability to find the noise after eliminating the bias drift. Crosslink is also called dynamic noise finding, which is robust to temperature drift, but it puts higher requirements for the rotation system, which will increase the cost and complexity of the noise finder. Tagging is called static noise finding, which allows for an inexpensive router. In the paper, we are based on 4-position tagging to find noise, but the inconsistency of temperature drift between different positions restricts its admuse accuracy, especially for the devices with larger temperature coefficient. The second part introduced the overview of MEMS gyroscope. The figure 1 shows MEMS gyrosystem architecture. This paper proposed 3 temperature compensation strategies based on CMOS sensor output and drive frequency and the gain control voltage. And the automatic gain control circuit regulates the oscillation loop gain to sustain the oscillation and generate a constant oscillation velocity. Phase-sensitive demodulation with a low-pass filter in the digital domain recovers the input angular rate. This work uses a novel high-precision frequency readout circuit. Figure A shows a typical island variant plot on the adopt not finding MEMS gyro. It reached the barrier instability of 0.08 degree per hour. This result is majorly limited by the noise flow in the gyro system, and they are almost identical from day to day. However, the temperature coefficient of MEMS gyro could vary greatly because it suffers from the mismatch distribution in the wafer and the uncertainty in package. We calculate the temperature coefficient of 50 MEMS gyro from the same wafer, which spread from 1 to 30 degree per hour per degree Celsius. So different temperature compensation accuracy is needed. The third this part analyzes the main noise that affect the above 3 temperature sensors. The traditional CMOS temperature sensor suffers from the trade-off between pink noise and area. In addition, in the process of analog to digital conversion, the pink noise of the converter reference voltage will also be contacted into the digital signal. And the gain control voltage still suffer from the pink noise, but its laser temperature sensitivity results in a better temperature instability. For drive frequency, which is immune to the pink noise in the CMOS without circuit, the temperature instability is better than the above two temperature compensation strategies, as seen in the figure. But an additional frequency without circuit and an external crystal oscillator are required. To verificate the compensation effect, we collect the gyro output, gyro's output statically at the room temperature, as seen in Figure A. The gyro's output has obvious temperature drift, but after compensation, the drift is surprised, but the bias instability of the gyro output is worsened. The Figure B shows their Allen variance plot. The compensation based on drive frequency has the lowest bias instability, and the gain control voltage is the second. Well, the temperature compensation based on CMOS temperature sensor had a significant impact on the gyro's output noise, which worsened the gyro BI from 0.1 degree power to 0.25 degree power. We did full position tagging 10 times. The output can be seen in the Figure B. In the process of not finding, the gyro's output has temperature drift. Then, using the above 3 temperature compensation strategy, compensates for the drift. Before the compensation, the standard deviation of ADMUS is about 0.47 degree. After compensation of gain control voltage and drive frequency, the standard deviation is reduced to 0.35 degree and 0.26 degree respectively. The conclusions of this study are given in the paper. This work analyzed the influence of different temperature compensation strategies on the BI of MEMS gyro for not finding, and the selection criteria of temperature sensor for mice-produced MEMS gyro with different temperature coefficients is also proposed, as seen in the table 1. The second virtual measurement based on the gain control voltage can replace the conventional CMOS sensor due to its higher temperature sensitivity and lower temperature instability. Virtual measurement based on drive frequency could be suitable for the gyro with higher temperature coefficient to implement ultra-low noise temperature compensation. That's all. Thank you for listening.